Thank you, sir. So good morning, all dear participants and our respected coordinators and experts. So today we are going to start with our day 3 sessions. So before starting the session, there is a small announcement for all the participants. We request you to please check the drive link. The hands-on material for today's session has already been uploaded in the day 3 folder in the drive link. So you can download the hands-on related details from the drive link. And this is a small request again for all the participants. We are getting requests regarding the attendance. Please note that the attendance will be marked against the registered email ID, because if you log in through different email IDs, it will be difficult for us to track the attendance. So it's a small request to all the participants. Please make sure that you are joining this WebEx event through your registered email ID. Today we are going to start with our first hands-on session. The hands-on session is being delivered by Kaushalendra Shishodhia sir. Sir is the director of Uniconverge Technologies Private Limited and is working in the area of IoT, AI, ML Industry 4.0, 4G, 5G. He is a partner of E&ICT Academy since 2019. We are proud to say that Uniconverge Private Limited has delivered many courses with E&ICT Academy. In the last summer, we have delivered the joint FDP in IoT and 5G communication with a very good response. Then we have delivered few free webinar courses with Uniconverge Technology, as well as we have done the training and the internship program with them. Sir is an alumni of IIT Kanpur and has been working in Ericsson India as a senior tech lead. With this short introduction, we would like to invite Kaushalendra sir for the session. Sir, please.
Yeah, okay, ma'am. So thank you. Thanks a lot, ma'am. So let me reshare my
Thank you, sir.
screen. Yes, ma'am. So can you see my screen now? Is it visible?
Yes, sir. Yes, sir. We can
Okay,
see
fine,
it, sir.
fine. Okay, fine, ma'am. Thank you. Thanks a lot, ma'am. So, good morning, everyone. Let us start with the first hands-on session in the series of advanced communication and antennas webinar and FDP program. Let me make it down. Okay. So already Froja ma'am has introduced me. So let me quickly recap my brief introduction. My name is Kaushalendra Sodia and I am IITK alumnus having 19 plus years industry experience. Right now working as a director at Uniconverge Technologies, and I am also working as chief mentor of IoT Academy for skill development. And prior to this, I have worked with many MNCs. Already Froja ma'am has already told you. So let us see the today's agenda. So first, there would be two major topics that we would be covering. One is modulations, and the another one is the receive diversity system. So in modulations, we would be covering the phase shift keying and the amplitude modulation, that is quadrature amplitude modulation. So in PSK, we would be covering BPSK and QPSK, and QM, it could be any for QM, 16 QM or 64 QM. So we would be taking one case in QM scenario, and we would be checking the performance of these modulation schemes in case of AWGN channel and the fading channel, that is Rayleigh fading channel. And first we would be rechecking the theory part, that what exactly it is mean. I think a lot of things you have already covered in last 2 days, and you would be having prior knowledge also about these modulation schemes. And then we, after quick theory, we would move to hands-on session. And in the next part, we would be checking the receive diversity system. It is in case of the multiple receive antennas. So if we have multiple receive antennas, there could be multiple options that which antenna stream we should take for the final decoding. So that is depending upon the selection, equal gain on the maximal gain combining. Again, here we would be checking the theory, and then we will move to hands-on session. So before moving to anything, let us set a context that what exactly we are talking about, which communication systems we are talking about. Because right now, you know that it could be anything. It could be a local sensor network, or it could be cellular network. It could be satellite communication. So there could be like wherever we have to communicate, there could be enormous use cases. But here we are majorly talking about the cellular systems. Whenever we talk about the wireless system, it is like scenario for the wireless channel propagation, it is same. The behavior is almost same. Uh, but if we talk about the cellular system, we have like some typical scenario where we have to we have multipath effects, Doppler effect, shadowing effect, reflection, diffraction. So a lot of kind of path losses are there, and additive white Gaussian noise is always there. That you are already aware. So here, when we talk about the cellular network, so cellular network means when the data is sent, the communication is between base station and the mobile. And why we are talking about all these things, why we are looking into the wireless system communication system performance, what is the need, what is the motivation? The motivation is that it is because of the ever growing demand of high data rate. So you know that earlier it was 2G, then it was giving some data rate, we were having only like voice calls or the text messaging. Then 3G came, we were needing more data. After 3G data rate, it was giving up to 384 kbps or 2 Mbps. And then 4G came, that is giving up to 14 Mbps, or up to sometimes they say with multi-carrier case they can provide up to 80 Mbps also, or 100 Mbps we can say. Now 5G we are talking about. So why there is a need of high data rate? Because we have lot of applications nowadays. We have multimedia applications, and like we have navigation application, gaming applications. So everything has to be real time. So we need more data rate, and more data rate means everything has to go through the wireless communication channel. So we have to have very robust wireless communication way of so that we can retrieve the original signal at the receiver side. So these are the like what kind of challenges we face and how can we tackle them. That is we would try to address during the complete session, today's session, and the upcoming session in the next week. So this is the typical network architecture in 2G, 3G, 4G. So the red one, the rightmost side, it is 2G, the middle one is 3G, and the leftmost is the 4G. I want to like why I am mentioning all these things. Probably this may be out of context, but ultimately whatever we are going to learn, that has to be productized. It has to be used somewhere. So I am trying to show you the context where ultimately these knowledge would be used. So if we talk about 2G, there is if we lower hand side BTS. This is the base station. It is talking to mobile base station. This is the only end mile communication that is wireless. The remaining communication when BTS is talking to other controller, BSC base station controller or MSC, the mobile switching station, and at the back end side when it is talking to PSN, all these things are wired communication. Either it is on optical fiber or broadband or whatever it is. So it is that one. The only wireless communication is between BTS, the base station, and the mobile. The similar way, the terminology changed when we moved to 3G. BSC was called RNC, and base station was called Node B, and there we were having the wireless communication. The similar, if we talk about 4G, the naming was little bit changed. We moved completely from circuit switch to the packet switch scenario. So that at the backend side or the core network side, you will see there is some architecture changes. So our interest is not at the core network side. Our more interest is towards the wireless communication where base station is communicating to the mobile. So today we would be discussing the AWGN. So AWGN means additive white Gaussian noise. So why it is additive? Because it is intrinsic to the system. So and its nature is to be additive to the signal. So that's why it is called additive. Why it is because it is distributed in all the frequency bands as we have the white color. So that's why it is called white. And Gaussian is because it has the normal distribution in time domain. So that's why it is called Gaussian. If we plot all the samples in time domain, it would have normal distribution. That is the Gaussian one. So that's why the noise behavior in a wireless system is called AWGN. And then we have relay fading. So the noise is additive. The fading is that would scale up the signal. So it will bring down up or down to any extent. That is called the fading part. So relay fading is why it is it is relay fading, not any other fading, because here we are talking about the complex signals I and Q, and I and Q both are independently normal distributed. So if we combine two normal distributed signals together, they gives a behavior of the relay fading. So that's why in relay wireless communication, the fading phenomena is mostly relay fading. Radio path propagation, this is path loss and other multiple path effects are there. Doppler effect is there, thermal noise, hardware calibration, multipath effects. So these kind of multiple distortions are there in the wireless communication, and that I think you would have seen at multiple places. This kind of picture we have. Line of sight signal is also there, and then some reflected, deflected, and multiple replicas of the original signal would be received at the receiver side. So this was a typical scenario, but other than this scenario, there are some more problems that have to be tackled in the telecom system. One is a TX power limitation. This is also called the near far problem. When we transmit the power, the base station is transmitting the power. How will it know that how with what power it has to transmit to the UE or to the mobile? Because it doesn't know the if it is within that cell, it would not know where the mobile is located. So if the mobile is nearby, if it is sending with the same power, it would be a problem to the to the other users, because the, the more power would interfere the other signals. So in cellular systems, keeping the low power is the primary requirement, or we can say we have to have the optimal power, optimal transmission power, because more power would ensure that that particular user will receive the data or the signal, but it interfere the other users. So this is the like a rule of thumb that we have to have optimal power to be transmitted, so that only that user should listen it and other users should be minimally interfered. And then there is a own signal interference, other signal interference. This own signal interface we would be checking in the next week hands-on session, where we would be seeing that there would be multiple channels within the spread spectrum, because next week we would be looking into the spread spectrum side. So how many channels could be there? So the same UE can have multiple channels and it would be interfered by other channels within itself. Then other signals means other user signal. Then maximum data rate mentioned. Okay, this is maximum data rate mentioned by an operator is the one that is very much in the ideal condition, when mobile is not moving, there is only one mobile. So when we say that say Airtel is giving 100 Mbps, so 100 Mbps is giving in a particular scenario, in a very much ideal scenario, when there is only one user sitting very close to the mobile tower, and it is not moving at all. So that in that scenario, the maximum data rate could be achieved up to 100 Mbps. But if there are more users, then the same data rate would be shared by all the users. Then the noise has the bursty nature. It comes in a burst. So how do we handle that one? Then we have we have multiple modulation schemes when we use the real telecom cellular system. We use multiple antennas, we use diversity. So all these terms we would be looking into in the coming hands-on sessions. So this one we would look in the next one. Now we will move to the hands-on part. So if you people would have received the files that I have shared, so we have to start with the let us move to the MATLAB part now. We have to do the hands-on with MATLAB. So, Firoza ma'am, have you shared the files with all the participants?
Yes, sir, the files has been shared in a drive link.
Okay, so please everyone download the files from the given link. I can wait for a few seconds, and if you download, it is called as FDP underscore day 3. So please download in a folder.
So participants, the materials are uploaded in a day 3 folder of course material. So please download it from there.
So once you download the files, you will see. I can show. I can go to the folder also. So once you download the files, So you will see these 4 folders inside the main folder. So we have to start with the first one, the bar for BPSK in AWGN and relay fading. So you have to download some at some location in your PC, and then you have to open the MATLAB, and you have to go to the path where you have, if you have downloaded, you open the MATLAB. You have to click this, or maybe you can check from. You have to go this way. You have to click this button, and you have to select the right path from here. So if you go to FTP underscore day3, you have to go to the first folder, that is one bar underscore BPSK AWGen relay. So if you select this one, select the folder, and then you reach here, and left hand side at the where you see the browser here, uh, you have to click the first file, that is, you will see 3 files, test1, test2, test3. You have to click the first file, that is test1 bar underscore BPSK. So we would be running a very simple test scenario where we have generated the BPSK modulated symbols, and we would try to demodulate them. So this is the first file, and let me show you the people who have not installed MATLAB. Please check carefully what I am doing. I will explain each and everything, all the steps here. So we have to run this file, and you will see that here we are printing the bit error rate. Bit error rate is 0, and I will show you what exactly we are doing inside the code. We are taking say 10,000 samples, and we are generating the some uncoded bits. So this is the raw data that the, or we can say it is the user data that has to be transmitted from transmitter to the receiver side. So this we have taken some random values, we have generated random values, and then we have done the BPSK modulation. And how do we do the BPSK modulation? It is uh, we have to modulate 0 to 1 and 1 to -1. That is the BPSK modulation. So here we are doing 0 to 1 and 1 to 0 status update, and then the same data we are assuming there is no noise in the first case. This is the ideal case where there is no noise, no fading. So we can say the receiver and transmitter are very closely connected, very tightly connected. There is no channel distortion. So the whatever we have transmitted, it has been received at the RX side, and then RX side we have decoded it like BPSK. How do you decode? If it is, I can open the. So if we talk about BPSK, it is kind of if we talk about the constellation, it would be binary constellation. So all the data would be either scattered here or it would be scattered here, and then we would be having a threshold value under which it would be a one level, and above that one there would be another level. So if we say that above the threshold it would be 1, and below the threshold it would be 0. So because it is BPSK binary phase modulation, it is very easy to judge that what was the actual transmission happened. So here the same thing we are doing. We are checking if it is less than 0, then we are making it 1, and if it is greater than 0, we are taking it as 0. So we are converting it to 0 and 1. So it is kind of demodulation, very simple demodulation that we are doing, and then we are trying to check what is the difference. It was the uncoded bits, it was the user data that we had transmitted, and this is the received data RX2 that we have decoded after. And if we, here we have plotted the difference, plot difference. So plot difference, if you see, in the figure, it is all zeros. So here When there is no AWGN noise, there is no fading, no distortion, we are able to recover perfectly. So this was the first very simple uh, test in the ideal condition. Now we will try to introduce some noise in this signal. So the next test 2 is introducing some noise. It is introducing AWGN noise. If you open the test 2 part, I could have taken Simlink also, but Simlink is very much here you can do more things. You can write your own script and you can like simulate in much better way. In Simlink, there is like sometimes I feel limitation to whatever they have given. You have to use those toolbox only. So by writing your own code, it is easier to like make it very generic and more exhaustive. So here, when we are adding the AWGN noise, so when noise is coming, then SNR, the signal to noise ratio, it is automatically comes into the picture. So and one more thing, okay, I would like to discuss. I think you would have heard about the Shannon theorem, right? Theorem. So everything is under the Shannon theorem. So Shannon theorem, what does it exactly say? It says that the capacity equal to capacity of a particular channel is equal to the bandwidth of that channel and log 2 1 plus S by N, signal to noise ratio. So this is the Shannon theorem. So whatever data rate, the maximum data rate we can achieve, it is according to this one. So what we can do, the bandwidth is always like it would be fixed. Once you have decided that this channel you are going to use, it would be fixed. What uh, flexibility we have, that is with the SYN, the signal to noise ratio. So how much noise we can handle properly, we can achieve the more data rate. So the all the communication theory from 2G to 5G, everywhere we are handling SYN. And there are more factors also. When there are like a number of antennas comes, number of antennas, then it would be multiplied by number of antennas. That is another thing. If uh, and and if we have more number of carriers, then it would be further multiplied with those many number of carriers. So this would be the generic formula for the Shannon theorem in context of basically 4G and 5G, because in 4G we have multiple carriers and we have multiple antennas in 4G and 5G. 3G also we have multiple antennas, but we are very rarely using multiple antennas. Mostly the number of antennas are used in 4G and 5G. So this way we can like increase our total data rate. So by increasing the number of antennas, by increasing the number of carriers, and by improving the SYN. So whatever we would be doing, it is to improve SYN. So today's exercise is about SYN, signal to noise ratio. So here in this case, we are taking signal to noise ratio from 0 to 40 with a variation of 1. So it would be incremented by 1. And here we are running this complete loop for each SNR case. So first let me run this thing and then I would explain you so that you can know that what exactly we are going to do. So I have run this program and here you can see here we have plotted the signal to signal versus bit error rate. So bit error rate is the one that whatever we have received versus whatever was transmitted. So whatever is difference between the two is called bit error rate. How many bits are in error? So for BPSK case, if we have low SNR, zero SNR means the signal power and the noise power both are equal. So that in that case it would be the 0 SNR. But as we move, if we increase the signal power, so SNR, if SNR is increasing, it means the signal strength is increasing, or we are better handling the noise. So noise is getting reduced and signal is increasing. So if we SNR is going up to 8, then the bit error rate is also reducing. So what is the ideal condition? When the noise is 0. So if noise is 0, the bit error rate would also be 0. But in case of low SNR or the negative SNR, the bit error rate would be more. So here BPSK is the one this was the case for BPSK. I would explain you what exactly we have done in the code. Please, you also run because you have code. It is very simple to run. If you have any questions, I can check on the chat window also. If you have any question, please write down on the chat window. I will check if you are asking, you are facing any issue. So I will check on the chat window. So far there is no question, I guess. Or more Q&A if I check. Okay, so there is no question as of now. So I hope that people are able to follow the instructions and they are able to run the code, because code is there. You need not to write anything. You have to just you have the code and just you have to click the run button and the code would run. So here we are running for all the SNR cases, that is 0 to 40, and we are generating the uncoded data, or we can say the user data, that is again the random data. The similar way that we done in the previous case, here we are again doing the BPSK modulation 0 to 1 and 1 to -1. So 0 is mapped to 1, 1 is mapped to -1 by using this formula. If you check this formula carefully, it would do the BPSK modulation. And then we have to generate a noise. So for noise, we have this rand function, the random normalized values it would generate with a range of 1 to n, and uh, then we would be having a real part and the imaginary part, because this is the complex number. So this way, this is n. You can also put the breakpoint here. If you put breakpoint, I can show you that how the things have would look like. So uncoded bits are something like this. It is all the 0 and 1 pattern, and we have 1 cross 10,000 values. So this is the data length that we have generated for testing it. So we are actually transmitting, this is the user data that has to be transmitted to receiver side. So, and after BPSK modulation, it would look like this one. So 0 is mapped to 1 and 1 is mapped to -1. So that is BPSK modulation. This BPSK modulation we have done. And then we are going to generate noise. So if you see noise here, I will do, so this is the noise. So noise is complex number, and now this noise would be added to the actual signal. So here we are adding at the receiver side. What we are doing, this is the transmitted signal that we have generated earlier, that is this one, and then we are adding the noise with the SNR case. So here this is the noise addition. It is happening the AWGN kind of thing, and now this is the received signal. Received signal would look like this one. So this is the received signal, and if we check the transmitted, it was like this. Transmitted was like this. The receive is some the real number, or we can say it is non-integer number because of the noise effect. And now we are doing the BPSK demodulation. So BPSK demodulation, as I told you, that since we have only two constellation, we can easily draw a line. We can easily define a threshold for which we can define that what exactly level it is. It is 0 or 1. So if above that threshold, we can define it 0, and below that threshold, we can define it 1. So the same thing we are doing here. And then finally we are checking the bit error. So this is the RX2 by the received uh, signal, and the uncoded bits is the original transmitted signal. So if I show you, this is the original signal, and this is the this RX2 is the received signal. I will come in the next step. So this is the RX2. Now what is the difference? It is something like this. So you can see that some bits are still in error. So wherever you see 0, it means it is without error. Where you see 1, so this is in error, the like 7th, 8th value. Then there are some patterns you will see in between 1 and -1. So those bits have gone in error because of the noise, in fact. So if I draw this plot here, here we are plotting it. If I continue, okay, it is doing for all the SNR cases. It will go for 40 times because the loop is for 40 times. So let us come outside. So here we are plotting here, and you can see the bit error probability is given, has been printed here. So bit error probability is the one that how many bits were in error divided by the total number of bits. So this is bit error probability when it was 0 SNR, and as we are going down, the SNR is increasing. So if the signal strength is improving, it means the bit error probability would go down. So if you see, you will see that all the values are going slowly down. So after some time, all the values have become 0. So it means when the signal was the significant enough in compared to noise, we were able to recover the transmitted signal properly in case of the white Gaussian noise. So here now we would be plotting it. So I will show you that the plot is like this. So all the okay, probably it has printed only one, the last one it has printed. We could have done the similar thing uh, uh, because we have printed in the last, and in last one the error was 0. All the error was 0. So it has plotted only 0 part. So we will see in the next exercise. It would be showing like more. If we take this picture inside, I can like show you that how it would look like. Take it here, figure. If you put figure, it will create a new figure, and then you plot here inside the loop. So for every SNR case, it would be printing. Let us reduce the length. Instead of going to 40, we can say run for say 15, because it would create so many images. So I'm running again here. So you can see different images have been generated. So when this is with high SNR, sorry, this is with 0 SNR case. 0 SNR case, there is so many bit in errors. This is the figure 1, and then let us open figure 2. Figure 2 is this one. Here the number of errors are little less in compared to, because here the SNR is 1, signal to noise ratio is 1. Here it was 0. Then 3 case, you can see it is further reducing. 4, further reduction. 5, 6, 7. So it means the signal is improving. Signal is having a significant role in compared to noise. Here very few errors are left. By the time we reach to 9, I think all the errors were gone. So with SNR 9, we were able to perfectly recover the transmitted signal. So this is the in case of the AWGN for the BPSK case. So I will close all. If you put close all the images, will be closed. All the figures that were generated, those will be closed. And if you put clear all, it would clear all the data that is and that has been generated intermediately. It is, you can see at the left hand side in the workspace side, all the data has been generated, is shown here. You can open anytime any data, and you can check the values also. Like if the bit error rate, if you want to check, bit error rate is this much, and the size of bit error rate is 1 into 15, and it is the double value. We can close the bit error rate, and then uh, if we print clear all, it will clear all the variables that are present as of now. It would clear everything. Now we can, so we have done, we have seen the BPSK performance in case of there was no channel impact, no impairment, no distortion. So it was covered properly, and there was no meaning of SNR in that case. We didn't talk about SNR when and we were just feeding the transmitted signal to the receiver side. But when we were adding the AWGN, we talked about the SNR. Now we would be adding relay fading also. So as I told, the AWGN is additive. We had added to the signal. Now we would be, when we are talking relay fading, it would be scale factor. So it would be kind of so if we the received signal RX, we can write in terms of H. H is the relay fading into TX, whatever the transmitted signal, plus noise. This is the additive white Gaussian noise. So representation at the receiver side in terms of the transmitted signal and the relay fading and the AWGN, we can do like this. Now this is the at the receiver side. If we are getting this uh, signal, then how can we? So what we have to do? We have to like do the if we have to find a TX, I can put star because it is not the exact uh, or cap, TX cap. This is the estimated signal at the receiver side. So how can we reconstruct that estimated signal? We have to take the complex conjugate of H, like H inverse into H into Tx plus H inverse. This is the formula I think you would have seen during the theory period also. So this way we try to reproduce, we try to recover it. So this is the matrix multiplication, and then this matrix is again multiplied with the Tx, and then sorry, this is Rx. Tx we have to, because Rx we are known to us. We do this one and H inverse n, then it would be we can recover the TX signal. I have removed intermediate, or you can write this way. If I talk Rx minus n is equal to H into Tx, and if we multiply H inverse both sides, so it would be something like H inverse x minus n equal to, so H inverse and H would be cancelled, then Tx would be here. So this is something similar kind of equation would come out. So we would be scaling down with the fading factor that is being applied to the transmitted signal. So let us open the test 3. Yes, test 3 here we would be adding relay fading additionally to here. So the same thing we have done, we had SNR from 0 to 40. Then we have the user data that we have randomly generated here. And then we have done the BPSK modulation. And after doing the BPSK modulation, when it goes to the ear interface, it would be having some relay fading. So relay fading, for relay fading we have used this formula H, and for noise this is the formula. So this all both are the complex signals. um, and then when we apply to the RX how it would look like H into TX, because relay fading would be in a scaling terms, and the noise would be in additive terms. So the RX would look like this. So let us run it here. Uh, I have put the breakpoints. I can show you. I will run it. Now the breakpoint has come here. We are generating some user data. That is the random user data with a length of 10,000. So it would be generating random data uh, uh, with maximum value 1, 0 to 1, and the length would be 10,000. So if I step it, so the data would look like this. Uncoded bits, that is the user data. One means the first row and 10,000 values, and the values are looking like this. And now we have to do the BPSK modulation. So BPSK modulation, after BPSK modulate TX, it would look like 1 minus 1. So earlier it was 0 or 1, but after BPSK modulation it would be 1 or minus 1. And for white Gaussian noise, you see this would look like this, white Gaussian noise, and the fading vector would be like fading vector is like this. We have to be very careful about the sizes. So all the vectors should be in the same size. If we have to do, if there is a mismatch in the vector size, we cannot do any mathematical operation in MATLAB. So now this was the three signals. This is the transmitted one is the noise, another one is the fading signal. Now all the three would combinedly make the received signal. So at the receiver side, we would be having impact of noise as well as relay fading. And here we can see the RX would be like look like this one. RX is like this, while TX is perfectly it was looking like this, but at the receiver side it has been distorted a lot. So now we have to recover from the received signal. We have to reconstruct the transmitted signal. We have to remove all the noise impairments. We have to remove all the fading impairments. So that we have to try. So one thing we are doing, since H was multiplied in the TX side and H is known to us. H is known to us. We will how H is known to us, that we would discuss in the next week hands-on session, because H is, how can we know it is not like, how can we judge that what kind of fading has happened, because it was done by the channel, it was not done by us, it was not done by the user. So how can the receiver know that what kind of fading had happened, so that it can cancel it? So this thing, how to estimate H, that we will do in the next session. But we would be having some estimation of H, and RX is known to us. So we can find a new value of RX. This is the processed value of RX. And now RX would look like this. So here we have removed some part of the fading effect after dividing with the fading channel. And now fading is done, fading effect is removed. Now for removing the noise impact, we have to the BPSK demodulation. BPSK was used for the noise removal. So here again we are checking, we are putting the binary hypothesis, that if it is less than 0 or greater than 0, and depending on that we are recovering the signal. So RX2 is the estimate of the transmitted signal, and this was the actual transmitted signal. So now RX2 is looking like this, and this was the original signal, this was the estimated signal. Now let us see what is the error rate we have achieved. So difference is somewhere we can still see there are some non-zero values. So non-zero values means there is those bits are in error. Here we are collecting all the errors and we are trying to check how many bits have come to the error so that we can find a single value for the bit error rate. So this loop will run for this we have done just now for the bit this SNR 0. But similarly we would be increasing the SNR for like because we are having a for loop here for the SNR. We would be doing the same calculation for each and every SNR up to 40, and we would be seeing that how much we can, how many errors we can correct with the increase of the SNR. So, and here we are, it has come again. So I would run the complete thing. I'm removing the breakpoints. So you can see this is the graph that we have achieved here. So the blue line here, blue line is the relay theoretical. The relay performance should be like this, but the red one is the simulated one. So after the relay fading, this kind of signal or this kind of bit error bit error rate we had achieved after the cancellation of the relay fading. So theoretical it was like this, but the way we had done, we had just like reverse scaled the received signal to counterfeit the relay fading, and we had achieved the bit error rate very close to the theoretical value. And the black one you can see it is for the AWGN part. So this plot we have done here down. So you can you can go through this code later on. So basically we have plotted whatever errors we have received, the bit error rate. The same bit error rate has been plotted here because bit error rate was stored for each and every loop. This was inside the for loop. We have stored in the bar vector. We are plotting it here down. So this performance of the BPSK you have seen with AWGN and the fading case. So here we can check more that after uh, if there is only AWGN, the bit error rate is coming down to 0 at SNR 10. So when we are having signal noise ratio 10, the bit error rate is almost 0. But if we have the fading scenario also, then the bit error rate is taking longer time, or maybe it needs more SNR to bring the bit error rate close to 0. So 40 also, when SNR is 40, we are not come close to the 0 BER. It is still there is still some difference. So removing relay fading, it is a little bit tricky. We use like very complex algorithm, or we use complex equalizers to remove this relay fading scenario in all the cellular systems. So this was a very simple case that I have shown you that we can just divide with the scaling factor, the Rayleigh scaling factor, to recover the original signal. But actually it is a very complex matrix calculation too, because there could be a like divide by zero cases also. So we do some Cholesky decomposition, and there are a lot of things we have to do. And for this, if we talk about to implement in the hardware, we use very good accelerators who can do this matrix calculation very fast. So all these things are implemented in accelerators or FPGA. So this scenario we have seen BPSK performance we have seen without any error. Then we have with AWGN, and the last case is recently we have seen AWGN plus relay feeding. So similarly, we can have for the QPSK. I have another code for QPSK. You can go into the second one, the QPSK relay. It is very much similar code. We can quickly run it. I am closing the other files from the previous folder. So here in QPSK relay, we are having AWGN as well as the relay feeding. But now instead of only like 2 points in the constellation, we would be having 4 points in the constellation because it is QPSK. We would be taking 4 symbols at a time, and we would be placing on the constellation diagram. So let me run it. So here again it is printing the bit error probability with the increase of SNR, and here it is showing all the figures. So it has shown all the figures. I will open one by one. So let us open with figure 1. So figure 1, this is the performance case. The theoretical one is the solid line, and for the simulated one that we could achieve is the circles. So we are very close to the theoretical value. So the performance of bit error rate with respect to SNR, we are able to achieve according to the theoretical value. The green one is for the AWGN. It is very similar to the one we had done in the for the BPSK case. Now we open figure one by one. This is the figure. This constellation is at the receiver side before doing any like cancellation of the noise or cancellation of the relay feeding. This is the pure signal at the antenna label. So we see with SNR 0 where signal label and the noise label were equal, the constellation was completely distorted. So all the signals were like they cluttered at the same place, and it is very difficult to check that where is the four. If we talk about the four symbols on the QPSK constellation, we cannot make it out. Now if we increase the SNR, it would be like this with SNR 2, 3, 4, 5. So let us jump to some other figure. Here still we have bad constellation. Here it has little bit started separating out. Let us go to 15. Here you can see little bit four constellation now, four symbols. One is this group, another group, and another group, another group. So with this is figure 15. So it is this is SNR 13 or 14. With SNR 13, 14, we can see little better constellation. Let us go to 17, is still bad. 19 is still bad. Let's go further, say 26. 26 it is better. You can see all the four symbols, all the four groups are very much clearly visible. Now you can put a threshold value, the hypothesis, so that you can make out that which each receive symbol is corresponding to which group. So it is very easy to do with high SNR value. It is very easy. So now we have to do processing in such a way, even for the bad cases where the this kind of signal is there, all the signals are cluttered together. We have to do proper relay, the fading impact cancellation, and we have to do the noise cancellation. So we have a proper like big complex equalizers in the at the receiver side to handle all these impairments. So let us check the code quickly. So here we have done the user data generation as earlier we have done. The only difference here is the QPSK modulation, that is here. There we had changed 0 to 1 and 1 to -1, but here we have to take 4 symbols at a time and we have to map it to the sum value. So this is QPSK modulation we are doing. The remaining things are exactly same. We are doing the relay fading and the noise we are doing in addition. And then this was the receiver. At the receiver we have received this kind of signal, and then we will start doing the equalization. We would cancel the relay fading, that is by this, and then we would be doing the hypothesis so that we can do the QPSK demodulation. So we have to take like 4 symbols, like two bits at a time, because that would make the 4 combinations. So we have to decode two bits at a time, and then we would find the bit rate and we would plot it. So this is, I think you people can also try to run the files even in 1 and 2. So this is for the QPSK, BPSK and QPSK part, where we have seen the uh, the noise handling, noise AWGN and the relay fading. In the next week hands-on, we would be like discussing more about how can we better. Here we are seeing only the impact of this channel impairments, but how we can effectively handle them, that we would be discussing in the next hands-on in the next week, where we would be talking about the channel coding, block coding, and some other mechanism through which we can like better handle the noise scenario. This channel coding can handle only the noise part, but the equalizer part can handle the fading thing. So we have a multiple elements in a receiver chain to handle the fading and the AWGN thing. So we have done BPSK, QPSK. Now we would quickly look into the QM. So QM, it is very simple. I have not put the BR or BR fading. I want to show the constellation in the real case. If you want to implement bar and relay fading, you can add the code inside this one. So if I run this one, so this is the transmitted symbol for QPSK, and this is the error. And I think I have done the constellation also. Constellation is not. Okay, so this is constellation of that one. So this is for QM. Let me check which QM it is running right just now. Okay, so this is 4 QM right now. 4 QM we have running. Let us run it with the 16 QM or maybe 64 QM. So 64, if I have to do, I have to generate a symbol that is for that can take value from 0 to 63, and then I have to do the. Okay, this is for PSK I have done. So maybe I have this is for PSK. I have to do the QAM addition. So I am doing the 64 QM modulation here, and then I am doing the same signal I am directly demodulating with the 64 QM, and then I am printing it here. So let me try to run this one, and we have a scatter part also. Okay. So this is the figure 1 is the transmitted signal, and figure 3 is the reconstructed signal at the receiver side, and the figure 4 is the error. So we can see there is we were able to see we were able to reconstruct the transmitter signal, so bit error rate was completely zero. Here we have not introduced any noise or the relay fading. It is the ideal condition. The same signal taken from the transmitter side has been fed to the receiver side. And the constellation for the 64 QM is like this. So there would be like some data is missing because probably since we have taken the random data, and the random data set is not very huge. It is only for only 64 symbols at one time. So if we have a huge number of data, we can see all the points would be fully covered. So 64 QM, the vertical side you would see uh, 8 symbols, and the x-axis you would be having 8 symbols. X and Y, 8 symbols you would be seeing. That's how it would make the 64 QM constellation. So here we have done only the modulation, and then directly we have uh, put for the demodulation. If we add noise impact is not there, the channel conditions are not there, we have channel conditions. So this is exercise for you, that you can do the same thing as we have done for the BPSK and the QPSK case, at the bit error rate, at the AWGN and the relay fading in this file, and try to check the performance in both impairment pigeons. So this is seen we have seen the QPSK, BPSK, and QM performance in presence of Gaussian noise as well as relay fading. Now we come to the second part, that is the transmit the receive diversity. So receive diversity, why do we need it? Because as we discussed in the beginning of this session, as per the Shannon theorem, we have to increase the data rate, and that is because of the user want. This is the user requirement, that data rate should be as much as possible. So there is a limit for everything. S by n we can handle up to some extent. Then we have to have some alternate methods to increase the data rate. So that's how we had started adding the more antennas. We add antennas at the transmitter side also, receive side also, or it could be any combination, only transmitter side or only receiver side, or it can be both the sides. If it is both side, it is called MIMO, multiple input, multiple output. But if it is only the receiver side, we have like option for the receive diversity. So receive diversity means that it is we are adding some redundant information, or we are making the replica of the same signal. Replica of the same signal, it is being either transmitted from the transmitter end, that is called transmit diversity. But if we are having multiple antennas at the receiver side, it is called receive diversity. We would be receiving the same transmit signal through multiple antennas, and we assume that each antenna would be having little bit different pattern. And if we have the some errors has happened in one antenna, some other errors have happened on the other antenna, but ultimately if we combine all the signal coming to all antennas, there is a big chance that signal would be recovered perfectly. So that's how we use multiple antenna at the receiver side also. So now there is a question that we could have multiple options, that which antenna signal we can use. Either we can use all antenna signal, or we can use a particular antenna signal to reconstruct the transmitted signal, or to recover the transmitted signal from the received signal. So which one we have to use? So that is driven by the received diversity, and we have three options here. One is the selection ratio combining, selective combining, or we have the maximum ratio combining, and the third one is the equal gain for combining. So let me start with the, see, this is the selection and the maximal ratio combining. We have two antennas at the receiver side, left hand A picture if you look into this. So here there is one reader. We have to select one of the antennas. So if there are multiple antennas, we have to select one antenna, and we have to select the antenna that is having the best power. So that, because all the signals, they could be in a positive phase or they could be negative phase. Either they can construct also, and there is a chance that they can destruct also to each other. So there is a interference, the own signal interference also. So we have to be very careful in what scenario we have to use the selective combining, in what scenario we have to use the MRC, the maximum ratio combining, and when we have to use the equal gain combining. So based on the gain from each antenna, we would be selecting the best gain antenna would be selected in the selective combining case. For the maximum ratio combining, here the concept is the weightage would be given more to a uh, good antenna signal. It means wherever we are getting better gain, it is like based on the gain factor. So the antenna giving better gain, it would be having more weightage. The antenna that is giving less gain, it would be given less weightage. So maximum ratio combining is indicating that the best favorable antenna would be giving the maximum weightage. So here all the antennas would be combined together, but it would be based on the weightage. And here we would be after combining them, we would be feeding for the further decoding. So this is the two cases. The third one is the equal gain combining, where all the antennas would be having equal weightage. That is a special case of the maximum ratio combining. So this is the same mathematical representation of maximum ratio combining. So the selection combining, when do we use? When there is a feeding path with highest gain. So we would be using that particular antenna that is having feeding path with highest gain. And maximum ratio combining, all the paths co-phased summed with the optimal weighting to maximize the combiner output SNR. So here the combined SNR has to be maximized. That is the ultimate aim, to have the maximum ratio combining. Equal gain combining, in this case all the paths would be having equal weightage. So let us go through the hands-on session for this one. So if we open the fourth one, the received diversity one. So here you will see there are three files. One is the selection combining, then maximum ratio combining, and equal gain combining. We start with the selection combining. I close other files.
Hello, Kaushlendra sir.
Yes, ma'am.
Hello.
Yes, ma'am. Tell me, please.
Sir, the participants are requesting you to, if you can increase the voice because your audio is coming very low.
Okay, okay. Let me check if I can raise my. Hello, ma'am. Is it better now?
Yes, sir. Yes, sir. Now it's better.
Okay, okay. Yeah.
Yeah. Thank you, sir.
Okay, thanks. So, so we start with the selection combining. Uh, so here we have taken, say, number of antennas as 20. So if we take 20 antennas and we run uh, with different combination, like initially we take only one antenna, then we check the performance, then we take two antennas and we compare which one is giving the best gain, and we select only that antenna. Then we take three antennas and so on, we go up to 20. So if we are having 20 antennas, and then we will check whichever is giving the best gain, we will take that antenna signal only, and we will fed to the further decoding chain. So here we have taken uh, 20 antennas. SNR we have taken 1 to 5, and now we are running the loop for two cases. One is for the antennas, and the another one is for the SNR case. For each SNR case, SNR 1 to 5, we would be checking that how the performance is happening in case of the varied number of antennas. So we have generated, I will put the breakpoint so that I think the things would be better. Okay, let me check what happened. Probably it is not there. I will open now. Okay, now if I put breakpoint here, let us run it. Okay, okay, so I think we need to change the file name because I have to change the file name because it is not allowing to use one. So if you people are also facing, so you have to remove the one because MATLAB is not allowing to uh, have a digits in the beginning of the file name. I had written at the last moment so that I can tell that which one in what sequence we would be running. So if I have changed the file names here, the same thing would be reflected in the MATLAB also. Here you can see it is again has changed the name. Let us start with the selection combining. I put the breakpoint here, and so here we are generating the transmitter signals with SNR with the simulated SNR. So the values are all values are 0 here, and then okay, here we are generating the feeding channel. So feeding channel is looking like this. Then this is the actual signal we are generating here. So okay, the actual signal was we had generated here. The data is the actual signal where we have generated with the random integer, and then we have done the modulation also. We have made it this way. So x this is the actual signal that we are going to transmit now, x. And there is some further calculation we do some we put the Kronecker product here, and after Kronecker this looks the input signal looks like this, and here we are applying the feeding that was generated at this point. So feeding if we are applying, so after feeding the signal looks like this, and now we have to apply the AWJ. It should be the white, it should be additive one. So it would add this white noise. So after white noise, the signal looks like this. You can plot also. You can plot each and every signal by using the plot syntax. And now we are doing, this is the received signal. This is the signal that has to be received. At the receiver side, we have to find the power gain. So power gain, how do we do? It is H into conjugate H. This formula comes as I told you here from H, when we do this one, this from H inverse into H, the same thing. This is the actual gain at the receiver side. This is the gain. So this gain we have to find out, and then we have to use the same gain to select the best antenna case. So H inverse, here we are doing H into conjugate H, and we are finding the power, and we are finding the maximum power. So here you will see that this is a scalar vector. Uh, sorry, this is the vector one with the real values. And now from this power, we will try to find the maximum power, which is the maximum power for this is for all uh, the same thing we have to calculate for all the antennas, and then we will try to find which one is the maximum. So here we have seen that this is uh, uh, okay. Here we are comparing the maximum value h power with the all vector. Whichever value is the maximum, we are selecting that one. So h power is this one, and the h max power is uh, this one. So we are doing the h selection here. So after the of, from the all the antennas, we have checked which is giving the best gain. We have taken that one, and this is the kind of this is the reconstructed signal, and this is the ultimately effective SNR from all the antennas. So this thing we would be here we have run for SNR 1. Now we would be running from 1 to 5 by taking the J value 1. So we have taken with initial one antenna, and then the similar way we would be doing for, like, we would be taking two antennas, we would be selecting best out of the two. So similarly, if we go to 20, we would be selecting the best one out of 20. So this way we like do this the selection combining. This is called selection combining. And this is the final SNR that we are achieving. So this is the graph if we see. So with increasing SNR, or we can say uh, with the increasing number of receive antennas, the SNR would increase. SNR would increase, and this is for different. Uh, so with number of receive antenna, if we increase it, we would get better SNR. The similar way, if we run the other case, let us take maximum ratio combining so that we can have better comparison. So in maximum ratio combining, what we are doing here, instead of taking the best gain, we are taking all the gains from all the antennas. Here we are doing the conjugate of H. H is the scaling factor, and we are taking the scaling factor and directly multiplying with the received signal. So here, this is the based on the gain factor. So uh, again, if we talk about this formula, whichever give the best gain, that this is the gain factor. So if we multiply the same gain with the received signal, it means we are giving the more weightage to the signal that is having more gain. So this is the difference between selection combining. Selection combining here, we had selected the maximum power vector, while in the maximum combining we don't do this. We are combining each and every. So this is a single statement that is doing that is combining all the antennas path, and then it is doing the summation of that one, and the overall effective SNR would come out from this formula then. So if I run this one also, and let me try to retain, okay, let us close the previous, all previous close all so that there is no confusion. Let me run it completely. So this is for the maximum ratio combining, and if I probably we can write it here. Okay, this one, and then if I run selection combining, I can put a similar thing we can put here, the maximum ratio combining. And the third one is the equal gain, that also we can take so that we can compare properly. Okay, so there it is already there. So I can put different figures here. So figure one is for the selection combining, figure two is for maximum ratio combining, figure three is for, and I have to, okay, here everything is fine. I am not closing everything, otherwise it will remove everything already. So okay, so now if I run one by one, close this one, start with the selection combining. So this is for the selection combining number of antennas versus SNR, and then we run the maximum ratio combining. So we can also do the similar thing by putting in the same picture. I will try to do the same thing here. This is for the maximum ratio combining, and the third one is the equal gain combining. If we run, so in equal rate gain combining, I can show you how we are doing. Instead of multiplying with H, here if I show you the maximum ratio combining, we were multiplying the gain factor. H was the gain factor, that is, we can say, the fading gain. If we do the reverse of that one, it becomes the gain. So this we are applying with the received signal. But here in the case of equal gain, we are giving equal weightage to each and every one. We are not multiplying with the gain factor. So we are taking signal from each and every antenna, and we are just adding directly. So let us, so this is the three cases. Let us try to put in a single case. Then okay. So if I put I take selection combining, and if I put hold on. Hold on. So by the time I am fixing this one, please you also try to run at your end. I am trying to bring all the graphs on the same page so that we can better compare each and every one. Okay, so let us run it one by one again. It would be printing in the same figure now. So this is the selection combining, but it would okay overwrite that one. That is one issue, but anyway, let us see how does it happen. So this one of them is maximum ratio combining, another one is the selection combining. The third one, if we also run. So here we see the performance for each and every one. So the which one is each one that we need to print again to check which one is the one. But we can see there is a difference between all the three combining case. Uh, this is probably for the equal gain combining. This is for the section combining, and the topmost is for the maximum ratio combining. So maximum ratio combining gives the best result because it gives the maximum weightage for the most favorable antenna. So that the interference from other signals can be minimized, and it can be added in a constructive way, manner. There could be some scenario where the maximum ratio combining could be a little bit counterproductive, where the noise is too high, and or maybe uh, all there is no peak, no a single antenna is giving best result, or maybe all the antennas are always almost in the same range. So in that case, the maximum ratio combining could be a issue. So in that case, we have better to take the selective combining or the equal gain combining. That could be a better approach in high noise scenario. Better to take the selective combining. But when there is a low noise, low distortion, better to take the maximum ratio combining. So this is the thing uh, I I can check if there are more questions from you people. Uh, the one is not coming. Okay, please repeat the maximum ratio and equal gain combining. This I have to repeat. Okay, let us go through the code again. So I think this is clear to each and everyone that why do we use diversity? Diversity could be of like it could be at the transmitter side, it could be of receiver side, or it could be a combination of both. So if it is only transmitter side, it is called multiple input, single output. So, we can say receiver side only we are having one antenna, multiple input and single output. If we have a single antenna at the transmitter side and multiple antenna at the receiver side, it is called single input and multiple output. Okay, and if we have both side multiple antenna, it is called multiple input, multiple output. MIMO, that is the case. We discussed that once we have multiple antenna at the receiver side, there is a choice we have to make that in what combination we have to take the antenna signal. So in the selection combining, we take the uh, antenna signal that has the maximal gain or the most favorable gain. So let us check the code again. I will start with the selection combining. Here, here we have generated a signal and then we have modulated it. So data of length 1000 and then model, it is BPS modulation. And then we are sending, we would be sending through like multiple combination of antennas, starting from only one antenna, then we are going to two antennas, then so different iteration we would be using different number of antennas. So let us take the we take the first iteration. This is if I come here, this is the first iteration where we take k value is one as one, that is it means the SNR is one, and j is one, it means there is only one antenna. So here we have only one antenna, and if one antenna, there is no many of the selection, because we have to always select the same antenna. Let us, I will continue so that let it come the next time. Then here the k value is 2, so it means the SNR is 2, but the antennas are still 1. So let us come to the scenario when we have at least two antennas. So I have to run it. I will close this one and I will run it again so that we have value of J2. Now J is 2. I can move to here. So now we have two antennas and we have SNR value is 1. So there is a combination that at one side we have number of antennas varying from 1 to 20, and the same time SNR is varying 1 to 5. So for each antenna we would be running the simulation for SNR 1 to 5. So now we have to create the channel distortion scenario. So we have created the fading channel. So fading vector is looking like this, and then we have to create this is the signal where we this is doing nothing basically. Kronecker product, it is multiplying with the original signal to look like, so that it can fit into the we can do the mathematical operation according to the fading and noise signal. So here it is the same signal that we have seen earlier. So Kronecker, okay, so now we have we need, since we need uh, two antenna signal, it is bringing to that one. So if I show you here X Kronecker, so here it is this is for one antenna and this is for the second antenna. So the signal is looking like we have two signals from each antenna. So we have duplicated the signal here, and then now we are applying fading to it. So after fading, let us see the fading. After fading, this is CIN. So after fading, this is the signal that is having length of 1000, and we have the two rows because from each antenna we would be having different signal. Now we are adding AWGN for on both of them. So this I have done completely. Yes. Okay, it has gone out. So I have to do the same exercise again because by mistake I have pressed the continue button. Let me come again. So right now J, okay, so now J is 3. Let us, okay, continue with J3. So now J3 is equal to 2. Okay. So now number of antennas in this case are 3, and we are running with SNR2. I missed the few steps in between, or maybe I by mistake I pressed the continue button. Let us take this case where number of antennas are 3, and now out of 3 we have to select the best antenna, and we have to take the signal from that one. So 3 antennas, and the signal looks like this now. X monitor. So now this is the signal from 3 antennas. So we have 3 replicas, and we are applying fading here in all the signals. We are applying AWGN. We are finding the antenna gain for each of them. So H here is also, this is the gain factor. H1 I will also open. So this is the fading case because for each antenna path would be different. So we would be having different fading vector for this, for each antenna. The same way we would be having different noise vector for each antenna because all the paths are independent to each other. So we would be having different vectors. So this is the gain. If we have to find the gain, we have to do H into conjugate H that I had discussed here. This is the gain factor while doing the estimation of the transmitter signal. So we have, this is the gain, and this is this thing we have to, this is the noise factor that we would generally cancel using the channel encoding or the error correction codes, or we do, there are some other mechanism in this cellular that is called interleaving, that is part of that is a combination of interleaving and the error correction codes that and some up to some extent it is being it is also handled by the modulation schemes. So modulation scheme handles something, then error correcting codes we have, and the interleaving with a combination we can try to achieve a very good SNR at after the decoding stage. So this is the gain that we have to use for doing the selection combining. So here we are doing the same thing. Now H power, after this H power will look like this one because we have uh, H power. Now this is the scaled, each value is the scale, the real value. It is the real value instead of the complex value because here the H was the complex, H is complex, but the power is it is kind of I square plus J square, or real square plus imaginary square. That is the power, and that way we have calculated this would be the real value, and this real value we would be trying to find the maximum power here. So this H power is fed here, and let us check what is the what the value is being returned. So out of the three, so if we talk about three signals here, this was the original transmitted signal, but received one, we have to check. Probably this was, let us see which was the received one. So we have to, out of three, basically we have to select which one is giving the best gain factor. So we have to select according to that. So here the what we have returned, it has returned indication and Hmax value. Hmax value is out of H power, it has returned this one. Hmax value that is corresponding to 3.2.204. Let us see which value it would be. H power 3, I think it has selected the second one, 3.204, that we have, let's check. Yes, it has taken the second second antenna, that is 3.204, and then 2.9, 2.93, 3.73, and 2.83. So 2.83 and 3.73. So it has taken one out of the three antennas, and then so it would multiply this Hx value with the it would create another conical product with each of them. Each of it would multiply. Uh, I can show you how it would look like. So it has replicated the same vector three times here, and then we would be applying the we would be selecting the best antenna and applying on the received signal. So after doing this, we would be getting the one signal that the H power is 3 into 2, and this one is into. So it would be basically comparing the one that is matching with the what exactly it is doing. It has taken three vectors, similar three vectors, and the H power of these three vectors. It will compare these three with these three, and whichever is the true, the same value it will pick, and it would apply for the, it would select that one, and it would apply for the further processing, for the decoding processing. So there is a like MATLAB generally it works with the matrix operation on or the vector operation. So here to optimize, to quickly doing the calculation or comparison, the same data was replicated so that we can compare. It would be matrix to matrix comparison, and whichever is matching, that index would be taken and it would be fed to the further decoding. So that way, it is the MATLAB way of working. If we do the same thing in C programming or some other thing, probably we'll do in an optimized way. But here it gives a very good libraries. They may not be optimized, but those are very easy to use. So it is because of that we have created we have duplicated the same vectors for all the three antennas. So here the HSEC so H selection we have done based on the one that is matching with this one. If I show you the H value, H value, the second antenna is minus 1.66, then 0.875. So this was the actual H. And now let us check the H, what it is. So it is the same value. So it has assigned the the column from the H, or it has taken the vector from a matrix calculation which is matching with H power with H max power. So that way we have selected the antenna that is with it, and correspondingly we can do the SNR calculation, because now we have to use the H selection that is having the maximum gain. So based on that, we can find the SNR. So the difference between all the three is how do we do the selection of the antenna antenna signal, and finally how do we do the SNR calculation. So if we go to maximum ratio combining, everything is same as earlier, but here instead of doing the comparison, we take the complete conjugate of H, that is the gain factor, and we directly apply to the received signal. So basically, if I show you here, so there is little bit different nomenclature here. Y is the received signal. Received signal is Y. Okay. The like here we were having RX, like here we were having RX or Y. Okay. So so there are three cases here. Let us take one by one. So Y is if we have Y signal and we have to do maximum ratio combining. So maximum ratio combining, in that case, we have to take only the we have to multiply H inverse or H. So there is some mathematical calculation. Sometimes we take conjugate of H, sometimes we take the H into H inverse. So that I will explain you in the next webinar. How do we do the how do we reach to the conclusion where we have to use H and where we have to use conjugate H into H star. So basically, when we do the maximum ratio combining, this is also one gain factor, and we do take the conjugate of H1. So this calculation, if you see, if I expand it further, this is the H inverse into Rx. This is H inverse into Rx. So for Rx, or here Rx is Y. So the same thing we are doing here. Here we are applying the whole gain vector with the received signal. So instead of doing any like comparing with the complete gain, we have to apply the complete gain factor with the received signal, and we have to combine them to make the sum of that one, and then we have to use. So let us again check by putting the breakpoint here. So maximum ratio combining, here we have one antenna and we have SNR1. So one antenna has no meaning. I will skip further. Let us have two antennas, and with SNR1 we will go with this one, and then this is the Now we have X value. This is the transmitted signal with two antennas and AWGN is added. Then we have done, now this is the received signal. Y is the received signal for both the antennas. So let us check the Y. Y is looking like this, where we have two vectors, each for one antenna. The received signal where we have the AWGN as well as the relay fading. And now we have to do the maximum ratio combining, since we need not to we need not to select any particular antenna. We know what is the gain from each antenna. We have to just multiply the received signal with the respective gain, and we have to take the addition of each antenna signal. So here so here it is combined and we have a single stream here. So now uh, to here y was like 2 into 1000, but the combined one is having the single stream. So from two antennas, it has become the single stream. I can show. So now maximum ratio combining, we have to check the gain of this stream, and then we have to check the gain of this one. We have to multiply the gain independently to each stream, and we have to take sum. So after sum, we would be having a single vector. So single vector is looking like this, and this vector would be fed for further decoding. So for further decoding, we would be always having a single vector. Either we have to take one out of n numbers, or we have to combine all the n numbers, whatever thing we do, but ultimately we would be having only one stream that has to be fed further for the decoding process. And y record, whatever y combined we have taken, we need to find the SNR for the combined one. So here this is the overall effective SNR. So this was for the maximum ratio combining. The same way we can have equal gain combining, everything is same. And let us put the breakpoint here again, and let me put from there. So here J is 1. Now number of antennas are 2. We are so here X chronicle, if we see, there are two antenna signal coming, and then we have done the fading, and we have to write the AWGN. That is fine. Now we have to do equal gain combining. So here you will see that when we are combining, we are not applying any H. That was the gain factor. Like we were doing the maximum ratio combining, we were multiplying with the gain factor. That was the fading gain basically. Roughly, this all things are the estimation. See, we don't have the exact value. We have to estimate that what would be the gain factor, right? So if something it was applied like it has scaled by x, then at the receiver side we have to do 1 by x. So the same way, if we have the complex number, we have to do the conjugate of that one, so that we can retain the phase and other things, we can do it. So here, instead of doing the H scale, we have directly added the Y combined signal with a weightage of 1. This is the one. We are not giving additional weightage. So all the antenna signal are given equal weightage. They are combined like in a uniform manner, and the same thing has been uh, used for doing the effective SNR calculation. So this is, there is a difference between, I think it should be clear now, what is the selection combining, what is the maximum ratio combining, and what is the equal gain combining. So mostly in telecom, we are using maximum ratio combining. Very rarely we use the selection combining. Let me check again if it is clear or there are some more questions. Okay. Yeah. Okay. So I think this is for today. So next week we would be covering the channel coding, where we would be again we would be discussing the Shannon limit. So please look into the Shannon theorem, what exactly it says, and how the convolution code or the turbo codes we talk about, the error correction codes, how they are they come close to the Shannon limit. And and because these turbo codes are very much popular and used widely in 4G, 5G, we have a different variant of turbo code, but because of turbo code, it is like very beautifully designed. So that thing we would be covering, and let me check what would be the further agenda. So next week we'll be doing spread spectrum. So how this the spreading is done, how it is helping in reducing the noise. Basically, spreading helps a lot in doing the noise noise reduction, and then we would be looking to more ways of handling the fading part. How the receiver should look like, receiver design should be done to counter effect the fading. And AWGN, as I said, the spreading or spreading would take care of the noise part, as well as we have a mechanism of the error correcting code, the convolution and the turbo code. Majorly, we would be looking in the convolution code, but we would be like a little bit discussing about the turbo codes also, how the turbo codes are better than convolution code. And then, yeah, so uh, this would be the agenda for 22nd February, and 25th February we would be doing the antenna element and the array analysis, the signal analysis based on the different antenna elements, so that we would be covering. So this is for today from my side. If you have more questions, I am ready to take. Please run it. Probably I may have gone a little bit fast, I don't know, but since you have all the codes, you can run at your end, and I can give you my email ID. If you have further questions, you can ping me. My email ID is kaushal@uniconvergetech.in. This is my email ID. Please take it down. If you face any problem in running the code, and please play a little bit with the code. You try to make your own changes. I have given one exercise. Please try to implement AWGN and relay fading in QM case. You try to implement 16 QM or 64 QM and try to introduce the error, and try to demodulate it and try to check how much errors we are retaining it, and at what SNR level it is completely able to recover the distortion introduced in the channel, whether it is due to the fading one or through the AWGN. So I think from my side, I am done for today. That so, Roja ma'am, if I think there are no more questions, so we can if we can conclude in that case. I think Roja ma'am is not available. So please, could you please tell me that how many people were able to run MATLAB code that I had given? Did anybody able to run it? If anybody has run it, please let me know so that I know the label or like how much you are comfortable with MATLAB, so that in the next session would be more interactive. Even we can like we will try to have more interaction. So make sure that you also try to run. I will try to give the code in 1 day advance so that you can run before attending the session, so that you have more questions. Okay, so I think some people were able to run the code. That is really good. Okay. Okay, some people were not able to run. I could not do. So, okay. So I will. So, Mr. S.N. Sharma, what was the reason? Like, could you write that? Why could you not able to run it? Was your MATLAB was not installed, or what was the issue?
Yes, sir. Good afternoon, sir. So, sir, we
Yes,
can
ma'am.
have go the practice session or the question answer session, because the next session will start at 12:30, sir.
Okay, okay. So, ma'am, yeah. So I think from my side, I am done, and probably questions are. I have already answered all the questions. So, so I think we can conclude it now if there are no more questions.
Uh, okay, sir. So, dear participant, do you have any query? Please, can you put it in the Q&A section if required, or else we will conclude this session and we will start the next session at 12:30. Please, participant requested to put the question in the Q&A section. So there is. Okay, sir. So I think so there are no more questions in the Q&A section. So we are going to end the session for today, the first session. Thank you, sir, for the hands-on session. Hope we are having two more sessions on hands-on, so the participants will be able to practice. And we request you all to please download the hands-on detail from the drive link of day 3. And there are few small announcements for the participants. We are getting regular requests regarding the WebEx joining. We request you all to please check the drive link. The attendance has been uploaded, and we have marked the attendance against the registered email ID as per the announcement from the first day. So we request you all to please register from your registered email ID. Otherwise, the attendance will not be marked. Other course-related are already uploaded in the announcement of the drive link, as well as the study material available are already uploaded in the drive link. For study purpose, you can also use the YouTube link, which is available in E&ICT YouTube channel. So please request to go through the announcements and the notification given in the drive link. So we request you all to please take a break till 12:30 p.m. At 12:30, we will start with the second session for today. So thank you, Kaushalendra sir.
Yep. Okay. Okay. Thank you, ma'am. Thanks all for your patience listening and trying to do hands-on. So have a nice day. We'll see you next week on Monday. Thank you all. Bye bye.
Good afternoon.
Good afternoon, sir.
So what is
Sir,
the
actually,
status?
the
Hands-on is
first
still going on?
no, sir. So the first session was over by 11:45. So we have given a break, sir. So we are supposed to start by 12:30. So we inform the same to the participant.
Okay. So why 11:30? Why so less?
Sir,
Hands-on.
11:45. Sir, it was an
11:40.
introduction and the queries were properly been addressed. So there were no query also because in between the session, the queries were being addressed.
And hands-on on which platform they did? MATLAB?
MATLAB, sir.
Okay. Okay.
Okay, sir. Thank you, sir.
So you tell me when to start.
So we informed the participant that we will start by sharp at 12:30, sir. So almost everyone is connected. I think so 20 to 25 people they will join, sir, now. Otherwise, we are having 100 participants who are connected, sir.
Okay, okay. And have you
Thank you, sir.
shared the participation detail with ministry? They sent a mail.
Yes, sir. Yes, sir. We shared, sir.
So what is the total number combining three academies?
Sir, 227, sir.
227. Our number has not improved any further.
So 46, sir.
46. And what about the other courses that you planned that?
Sir, it is the registrations are ongoing, sir. So we are getting the response, sir. Okay, sir. Thank you, sir.
Yeah, yeah. Just tell me when to connect. Huh?
Yes, sir. Yes, sir. We will, sir. Yes, sir. Yeah, good afternoon, sir. Sir, we may start the session, sir.
So good afternoon, everybody.
Good afternoon, sir.
So I hope you all are enjoying the sessions, and already we had one hands-on session as well. So today's session we will discuss two very important concepts. One is how we transmit information or signal through the channels which are band limited, and then another important concept which is equalization. So to conserve bandwidth, I am stopping my video and sharing my screen. Is my screen visible?
Yes, sir, it is visible.
Now, how do I minimize this one? This creates a problem for me.
So which screen?
No. Okay, now it is gone.
Okay, sir.
Yeah. So it's visible. Screen is visible.
Yes, sir, it is visible. It's
Okay.
waveform designed for band limited channel.
Yeah. So waveform design for band limited channels, and it will be followed by equalization, the very basics. So what happens when we transmit the symbols? Usually our symbols are modeled as rectangular pulses, and you know that if you look at this from the frequency point of view, you require theoretically infinite bandwidth to transmit this type of symbol. The band limited channel, as you will see, will have frequency limitation in that sense that it will allow only a fixed band of frequencies to go through it. Now, if you remove in other way, it actually works as a filter which removes certain part of the frequency. Now, what happens when you remove the frequency components from a signal, and then if you reconstruct the signal in time, then the signal will actually expand in time, and we have fixed duration or symbol duration or bit duration. This is fixed. Now, if a symbol becomes longer than the allotted duration, it will shoot into the next symbol duration, and this will create a lot of problems. Fortunately, most of our communication signals systems that we design, these are sampled ones. We do not consider the entire waveform. Rather, we sample the waveforms at certain discrete points of time. Now, this expansion and overlapping of the neighboring symbols, this effect can be reduced if we can ensure that during our sampling instant, the contribution from those overlapped symbols, these are ideally zero, or at minimized. So this is the essence of the entire discussion that we are going to make. Can we really design the symbols which will not contribute significant amount of uh, interference at the sampling instance of the neighboring symbols? So this is what we will try to explore mathematically, and this is what we are going to do. So a band limited channel, it is modeled as a linear filter whose bandwidth with a bandwidth limitation. Band limited channels that are most frequently encountered in practice. In practice, most of the channels that you will use that will have bandwidth limitation. Your telephone channels for audio, we keep the bandwidth around 4 kilohertz. Radio channels, again, you are limited by the bandwidth of the RF stage that you can transmit. Satellite channels, underwater channels. So whatever practical communication system you take, it will be limited in bandwidth. It will not allow infinite frequencies to go through it. And in fact, bandwidth is a very scarce commodity, and we want to push as much information as possible through a given bandwidth. And later on, I think in some point of time, this issue will be discussed, the spectral efficiency, the bits per second per hertz that we can transmit. So a band limited channel is characterized by a linear filter whose impulse response Ct and frequency response Cf, these are, Cf is the Fourier transform of Ct, and in the frequency domain, the channel is said to be band limited if Cf does not have any component beyond some frequency Bc. So in that case, we say that the channel is band limited to a frequency, upper frequency Bc. Of course, it will be from minus Bc to plus Bc, the way we represent mathematically. Now, our transmission system model is shown. So we'll have our input data, and it goes through a transmitting filter GT, which works on it and produces a waveform Vt. This Vt goes to the channel, and then the noise gets added to the transmitted signal, and what we receive at the receiver is I, and then it goes through another receiving filter GR, and at the output of the receiver filter we the received signal Yt. And as I told that we are dealing with a sampled system, we have a sampler which produces YMT. Capital T is the symbol or the bit duration, and then you have this sampler. The sampling instant is decided by symbol timing estimator, which actually takes this Yt as an input and decides when the sampler should sample the signal. And finally, these samples are passed to a detector, which actually makes a decision in favor of some symbol. So this is how the entire system is organized. Just give me a moment. Hello. Okay. Sorry, there was an interruption. So the system consists of a transmitting filter with impulse response GTT and linear filter channel with AWGN. Now you know what is AWGN. We have discussed it in other lectures. A receiving filter with impulse response GRT, and sampler that periodically samples the output of the receiving filter, and a symbol detector. And this detector actually makes a decision that whether which symbol was transmitted from a given set of symbols. And our entire exercise now will be to make sure that at this sampling instant, the contribution from the other symbols which were transmitted earlier into the system, they do not contribute anything, so that we get the proper sampling value of our desired symbol. So for an AMRE PAM modulation type of scheme, the binary input data sequence is subdivided into k-bit symbols and represented by a waveform. So each symbol is mapped into corresponding amplitude level, which in turn modulate the output of the transmitting filter. So at the output of the transmitting filter, you have Vt is Gt, T is the impulse response. So An, Gt, G capital T, it is the impulse response T minus N T, where this T is the symbol duration we are talking. And so Vt is a sum of this. You can see that delay sum, and then associated received signal will be RT, and now it changes from GT to H, because we are combining both the impulse response of the transmit filter and that of the channel together, and we are adding noise, and HT is the impulse response of the cascade of transmit filter GT and channel CT. That means HT is the convolution of CT and GT. So we get RT written in continuous form. Now in the sample domain, we write YT is equal to AN XT, because this RT will first get convolved with our receiving filter, and then we'll get a signal X, and when it is sampled at empty time instants, we can put it in this form, where this X empty is GT empty, C empty, GR empty. So everything has been taken care, and this new empty, it is N empty, the noise convolved with the receiver, because this noise will go through the receiver filter. So this is our Y, and how we can write this YMT, because now you can see that it will have contribution from earlier symbols as well. It will have the effect of the channel included, it will have the effect of the transmit filter included, receiver filter included. So in the equivalent form, we can write Ym, T we are just assuming that we understand. So Ym is equal to X0 AM, and then summation of N not equal to M, An X M minus N plus Vm. So for every sample Ym is a particular sample which will go to the detector, and you can see that this sample contains this term Am which we are looking at, plus it contains this contribution and the noise term. The first term is the symbol Am which we are looking at. It is scaled by the gain parameter x naught, and second represents the effect of the other symbol. So this is quite important to understand. Ym is a particular symbol that you are giving it to the detector for making a decision, and you want to ensure that you present only Am to the detector or the scaled version of it. But what happens because of the band limitation we have talked about, we have reduced the bandwidth of the channel, the symbols have expanded in time, there is overlap, it actually going into the maybe next symbol interval. So we are getting this contribution which is called inter-symbol interference or ISI. And this term is the noise. Now we have seen the systems where you have actually discussed, I was attending yesterday, how to get the bit error rate and other thing calculated. When these two terms are there, your desired signal plus the noise sample are there, and then you can make a decision in favor of a symbol by observing it, and if you make this decision correctly, there won't be any error. If you make an error in that decision, you will get a bit error. But now we see that this additional term is also present at the sampling instant, and this is called the inter-symbol interference or the ISI. ISI causes the degradation of the performance of digital communication system. So noise is one form of impairment, and now when we consider infinite channel bandwidth, this factor will not be there. But whenever you will consider any finite channel bandwidth, this middle term also will come into picture. So how to get rid of this term? Can we reduce, can you make it zero at the sampling instant? This is what we are looking into. The problem of designing the signal with zero ISI at sampling instant is considered. So I am emphasizing this word again and again. At the sampling instant, you are reducing the ISI. ISI may be there, but you design your signal from the knowledge of the channel. You design your signal in such a way that after it is distorted through the channel, when you sample it at discrete times empty, at that time the contribution because of ISI is made equal to zero. So that is theoretically we will first investigate, and then we will see what solution exists and whether this solution is physically realizable, and if it is physically realizable, in what form it is realized. So we write Ym is equal to x0 am plus this form, the ISI and VMT. In order to remove ISI, it is necessary and sufficient that this term xmt minus nt is 0. Please note that x, we got the convolution from three terms. One is the transmit filter, another is the receive filter, and the third was the channel. Now, x mt minus nt, if it can be made 0 for n not equal to m, this condition, and if we take x0 to be equal to 1, which we assume that we could set the x0 is a gain term, we can adjust the gain in such a way that it is 1, then we will have only at the output of the sampler, which will go to the detector, is our desired symbol am plus the noise, which anyway we cannot, particularly thermal noise will always be there. So signal plus noise will be given to the detector, not the signal plus interference plus noise. So x and t, that means you require, you can put this n minus m minus n as a new index, x and t. We want this to be 1 whenever m is equal to n. Whenever m equal to n, that means x0 is equal to 1, and this is 0 when n is not equal to 0, that means m is not equal to n. So this type of a condition was analyzed by Nyquist, and he gave a particular condition that we can achieve this particular condition provided our x and t is a signal like this from m equal to minus infinity to infinity, x Fourier transform f plus m by t, this sum becomes equal to capital T. So that can be derived starting from this condition. So let us assume that this condition is there. Now what are the implications of these conditions? Let us see. Note that the output of the receiving filter is given by XF, I mentioned again, GT, GF, and GRF denotes the and CF that we have already discussed. And considering the channel has a bandwidth of W, CF is equal to 0 for mod F greater than W. And consequently, XF is also 0 for F greater than W. And this will lead actually to three distinct cases. If you go back to the earlier one, look at this condition. For you will get XF when m equal to 0, it is only XF. When m is equal to 1, you will get XF plus 1 by t, that is a shifted version of XF. X is equal to minus 1, m equal to minus 1, you get XF minus 1 by t, the left shifted version of XF. So you are getting a overlap or shifted version of this, and shifting is taking place at a m into 1 by t. So this is important. So suppose we take W is the band limit or up till which f is non-zero, and let us consider t is such that it is 1 by 2W, or equivalently 1 by T is greater than 2W. Now, if you look at this plot, XF is from minus W to W, and this is 1 by T, the next pulse where we have plotted, and in between there is 2 by T. So 2 by T is greater than W will actually, sorry, not 2 by T, 1 by 2T, 1 by 2T greater than W, 1 by 2T greater than W will ensure that these two will not overlap. And when these two will not overlap, you cannot design a system where this summation will become equal to capital T, because you need a condition when either they just overlap or they just touch each other, because you want this to be constant. This ZF, you want it to be a constant. This is just a representation of XF. So you cannot design it when there is a gap. Next is T equal to 1 by 2W. And in that case, essentially, you are talking of a frequency response which is of the form of a rectangular window. And this condition can be met, that XF is equal to T, and but the problem is, when you get the equivalent time domain signal, it becomes a sinc function. If it is a rectangular function in frequency, in time domain you get a sinc function, and this means that the smallest value of T for which the transmission with 0 ISI possible is T equal to 1 by 2W, and for this value xt is a sinc function. Now this type of sinc function, it becomes non-causal and non-realizable. To make it realizable, a delayed version of this is used, but it gives rise to other complications, the convergence, and then creating so rate of convergence of the pulse shape is slow, and tails of xt decay as 1 by T. Apart from that, there are other issues. I am not going into those. If capital T is greater than 1 by 2W, in that case we have the overlapping, and we can actually satisfy this condition in different ways. And this is what is utilized in design of the signal. The replications of XF are separated by 1 by T, and there exist numerous choices of XF such that ZF is equal to T. And one such solution, we will not go into the derivation of this, but we will display one such solution. A particular pulse spectrum which has desirable spectral properties has been widely used in practice is called a rest cosine spectrum. So you can see that the rest cosine frequency characteristics 0 mod of f 1 minus alpha by 2t. So over one region you make it flat, and then for mod f greater than 1 plus alpha by 2t it is 0, and then within this interval it decays as cos of mod f 1 minus alpha by 2t. So essentially the overlaps where there is a skirt of one pulse, there actually you will get another skirt of another pulse, and they will make it up and they will satisfy this condition that z of f should be equal to t. This parameter alpha is called the roll-off factor, and it can be chosen appropriately because you can see that alpha also decides the bandwidth, because 1 by 2t, alpha is 0 means 1 by 2t, the ideal case. But now you are introducing a roll-off factor alpha, that means your non-zero frequencies are exceeding that 1 by 2t. And for this, if you find out the corresponding time domain function, then it is in a realizable form. And this type of waveform design for transmission through a band limited channel so that you can minimize the ISI is very, very common practice, and major simulation tools like MATLAB and all, they provide you this block where you can set those parameters alpha, roll-off factor, and get the pulses of appropriate shape. So this is the pulse shape for different values of roll-off factor, and corresponding, as I was telling, that 1 by 2t, this frequency range it exceeds, and the next pulse will have in this range, so there will be overlap of frequencies. So this is in short how we can design the pulses. Sometimes this is distributed between transmitter and receiver, and we talk of root raised cosine pulses, so that when you take the product of these, you get a raised cosine. So pulse shaping is necessary, particularly when your channel is band limited, and all practical channels are band limited. Ideally, theoretical analysis, when you do with your only signal noise is present, that is a case where you are considering that you have all the bandwidth available for transmission of your signal, which is practically not true, because in all practical system it will have some band limitation. Even the most wideband channel also will be limited, but then its effect due to band limitation will be less as compared to a very narrow band channel where when you try to transmit high data rate. Another important task we perform is called equalization, which takes into account the impairment produced by the channel. And in fact, three things are used in tandem to overcome the limitations of practical channels like wireless channel. It is the equalization, it is channel coding, and in fading system, the diversity. So all three in many practical systems used together, or you can use them in isolation also. So we will discuss equalization. Again, is a very, very broad topic and involved lot of complicated mathematics. We will try to understand these basic concepts, and we'll see some simple examples so that we get the feeling of what an equalizer does. So converts channel induced distortion which produces ISI and precedes the detector of the received data. So before detection, you perform equalization. Equalizer may be linear, it may be nonlinear. In linear case, for example, it may be zero forcing or MMSE type. Some of the equalizers, they may be adaptive, they will periodically update their weight. And nonlinear equalizers, these are more complicated. I'll not attempt here. I'll just show you the structure. These are called decision feedback amplifier equalizers or DFEs. The equalizers, they may be symbol spaced or fractionally spaced. When we consider a linear equalizer, usually we employ a tape delay line, as you will see that the input signal is scaled, delayed, and then again delayed and scaled, and all these delayed and scaled versions, they are added up. So this step delay line, the delays may be set same as the symbol duration. So in that case, they are called symbol spaced, and they may be a fraction of the symbol duration. In that case, they will be called fractionally spaced. So we considered again the same system what we considered earlier. We are not showing the sampler and this thing. So you can see that you have the transmit filter, you have the channel, noise is added, you have the receive filter, and we assume that some pulse shaping has been done, and then it goes to an equalizer, and then it is given to a detector. Sampling is performed here, and you will have all these symbol timing recovery and all the other circuitry has to be there to do the sampling. So this is a linear transversal filter type equalizer. Here you can see that we have the delay units, and each unit is producing a delay of tau, which may be same as t or it may be different than t. And then the output of these delay elements, these are scaled by certain weights. These weights may be fixed, or in case of adaptive equalizer, that's why you put a more generic case, you will have some algorithm for adjusting the tape weights, and also you may actually use the equalizer output in those algorithms to find out the tape weights. We will see how that is done. So let us represent XF as GTF, CF, GRF, and G equalizer, let us write it, the impulse response as Cn delta T minus N tau, and the equalized output, it is written Qt is equal to Cn x of T minus N tau, and 2n plus 1, this is the number of tape weights we are using. Let the sample of Qt be taken as t equal to mt, and then we can write qmt as Cn x MT minus n tau. Please note that here we are not considering any noise, and this you can have at m equal to 0, plus minus 1, plus minus 2, plus minus n. Since there are 2n plus 1 equalizer coefficient, what we can do, as we did earlier, we can apply this zero forcing condition such that this C x mt minus n tau, it becomes 1 when m equal to 0, and this remains 0 when m is equal to plus minus 1, plus minus 2 n. So this type of condition is called zero forcing equalizer, and this equation can be put in the form of a matrix equation where these C's are to be determined. Q output, we know only one of the element will be 1, remaining element will be 0. X will be a matrix 2n plus 1 into 2n plus 1, and C will be a 2n plus 1 coefficient vector. So once you have put this equation in this form, now we can find out C, sorry, this should be small c, there was a typo. So C is equal to x inverse of Q. So ZFE ignores the presence of additive noise. It may result in a significant noise enhancement in the frequency range where CF is small, and we find that this GEF equalizer filter response is reciprocal of the channel frequency response, and therefore whenever CEF is very small, it will produce a very large gain. It will try to produce a large gain, and when you produce a very large gain, you also amplify noise. So noise enhancement is a issue with the JDPs, particularly when your channel frequency response, it has deep nulls. Now we ignored the noise. We can have another criteria taking noise into account. Let the noise corrupted output of the FIR equalizer, it is now denoted by Y. Just symbolically it is denoted. We are not going into the details. And YT represents the output, ZT represents the output of the equalizer. Sorry, there is another typo. Although it is understood, let me correct it, because otherwise I'll forget when I'll give the slides. And ZMT you can write in this form. Let M is the desired output at T equal to MT. Now this is the concept of sending some preambles or known symbols comes into picture. The equalizer is trained actually. So when you transmit a long frame, you reserve first few bits, for example, where you train the equalizer. Your detector receiving, and you already know what you are expecting in this particular symbol interval. So let MT with the desired output at T equal to MT. And the mean square error between ZMT and AM you can write as expectation of ZMT minus AM square, and then you can use the minimization of mean square error. Please note that this will result into, this is the expectation operator. It is the, you need to introduce the concept of the correlation matrices. You will have to actually compute. So I am not going into the details of this, but in principle you can find out a solution. These AMs are known and ZMTs are, these CNs are chosen in such a way, at least for the known AMs, this MSE is minimized. And once you do that, then you leave it for the rest of the symbols you transmit, and then you, if you train it periodically, then you can also have adaptively, when the channel condition changes, it is sensed, and then this type of coefficient adjustments are made. I take up a small simple example of ZFE to show how it works. For example, at the sampling instance x minus 3t minus 2t, these are the sequence actually. We have these values, x values, and it is plotted. So you can see that, say this is our desired output. Here we get, and then adjacent symbol durations we get the contributions. Now the ZFE will try to reduce this to, if we use a 3-step filter, then we will try to find out the coefficients so that these two are reduced to 0. So you can form X. So how it is coming? You remember our expression, it was X m minus n. So the first, our is a 3-step, so the first row will be m equal to minus 1, then 0, then 1. So if you put these values, x, the diagonal elements will be all ones where m equal to n, and then you will pick up the other values, and q, as I told, it is 0, 1, 0, and then if you calculate x inverse, you will get this, and then you multiply it with q. Since it is 1, 0, 1, 0, you will essentially pick up this column, and therefore your output C's will be, the coefficients of the or the tap weights will be given by this. And once you get these C values, you put back into your equation and then again recalculate, and then you will find that you are getting 1 at the desired sampling instant, other adjacent to instance it is 0. It is not contributing any ISI to the next adjacent ones, but there are small amount of ISI will remain in the symbols which are at far off, and that way the size length of this equalizer will decide how many sampling instance you can actually reduce the ISI. I also designed one small example in the form of a simulation to show you how we can play with these things and design equalizers using the zero forcing principle. For example, I have not considered any noise here. For example, we have a, is my screen visible?
It is visible.
So we have a random integer generator which feeds this BPSK modulator. Now your BPSK modulator will produce plus minus 1. Now this is our channel. What this channel is doing, you can see that it is scaling the symbol, and then it is again delaying. Z minus 1 is a one symbol duration delay, and then you are adding these two here. So the symbol and its delayed and scaled version is now added, and this is given here directly to the demodulator, and we see how much error we do get, and then we give it to a 3-tap equalizer. So here you can see that this is 1, this is 2, and this is the third one, and these values have been calculated so that the error we can put minimum. While comparing this, we will have to put one delay because ours is the 3-tap and our desired symbol is in the central one. So the input, if we want to compare with the, because we will get the output after one symbol, and therefore the input also has to be delayed by this, and then you can make a comparison. So let me run it for example 1000 number of bit, so that the waveform also I can show you. So you can see that roughly the equalized one, the bit error has reduced roughly 254. It is a 3-tap equalizer. It has its own limitation. So roughly 254 bits out of this 1000 are in error. But if you do not do any equalization, we are getting 50% of the bit directly into error. And this shows, let me. So this is what the modulator produces, and this is the way we have distorted the symbols, and then we are trying to recover them by doing equalization. So this is a simple example just to demonstrate how you can actually design these equalizers. The last equalizer, as I told, these are nonlinear type equalizer and complicated to analyze. Here we have a feed forward filter, then the detected samples, they are again fed back to another filter, and the output of this filter is subtracted from the incoming feed forward output, feed forward filter samples, and this difference is given to the detector. So analysis is really very involved. I will not attempt this. For details, those who are interested to go further into this, you can consult these books, Fundamentals of Communication Systems from Pearson's Education, written by Proakis and Salehi. Another very well-known book is by Zeimer and Trenter, which is Principle of Communication. Now I think it is the 7th edition is there, and John Wiley, they actually publish it. This is all what I wanted to tell about the design of the waveforms and some basics of equalization and how it can improve the system performance. There were some queries from previous lecture, yesterday's lecture, which could not be taken up because the network was not working properly. So one question was regarding the use of heads on theta and phi. These heads normally we use when we say that it is an estimate. And then another question was on the PLL. PLL actually detects the phase differ. It contains a VCO. A VCO is a voltage control oscillator. Suppose a VCO produces a frequency F for a given input voltage. Now, if you change the input voltage, then it will produce a frequency F plus some K into the input voltage. So the VCO output and the input signal, which is in the form of cos omega t plus theta, these are given to the phase detector, and the phase detector is essentially a multiplier followed by a low pass filter. So it will take the phase difference term and then it is given to another filter to generate this error term, detected phase detector output. It will come in the form of say sine phi minus theta, and if already you are tracking the phase quite well, then this phi minus theta, say let us denote by psi, this will itself will be very small, and you can give it to another filter which will produce the error voltage that is needed for the VCO input. Now these filter gains are adjusted appropriately so that you track the phase or follow the phase of the input signal as closely as possible. So this is in brief the how a PLL works. If you want to derive everything mathematically, I have referred to these two books. In both the books, complete derivation of the PLL system for different application, because PLL comes in different forms. It is used in demodulating FM signals. We have seen that you can use it for in squaring loop, in Costas loop. So in various forms it can be used. Nowadays digital versions are also available, DPLL. So you can get the details mathematical description of how it operates, because it will take a lot of time to derive everything. I just gave you the basic idea how it works. Essentially you have a phase detector followed by a loop filter, and then it goes to a VCO whose frequency is changed, output frequency is changed according to the input given, which is the output of the loop filter, and everything is to be designed appropriately. We have reached the end of our time. If there is any question in the chat box, I request Pubali to tell me the question so that We will try to give the answer if I know it immediately. Otherwise, maybe in some of our next classes, we'll try to discuss those questions.
Yes, sir. So like till now, there are no queries in the Q&A window. So participants, if you are having any queries regarding this session, please put in the Q&A section.
And we can take it up because I have another two sessions later. So they can think they've just gone through this. They can see also the YouTube feed, and if any query come, they can post it here. We'll take it up later.
Yes, sir. That can be done.
Okay.
Thank you,
Okay.
sir, for the informative session.
Thank you. Thanks all. I hope that because these are the things which are very, very important from practical implementation point of view. And we need to discuss more and more these aspects. How do we design the signal? How we equalize the signal? Because in practical communication system implementation, all these issues comes. And I hope my fellow colleagues who are teaching in different institute, if it is not there, they will introduce this type of topics in their syllabi as well. Okay, Pubali, can I?
Yes, sir.
Okay.
Thank you, sir. Thank you, Ratnajit, sir, and all participants and co-principal coordinators for joining the session. So an announcement for all the participants. So please try to register with your registered email ID only, as it is helpful for us to track your attendance, as it becomes difficult to track you among all the participants. So please try to maintain that from tomorrow onwards. And as Ratnajit sir said, in case you are having any queries regarding this session, so you may please think, and you can go through the YouTube session also. The same sessions has been uploaded in YouTube as well. The YouTube link is in the Google Drive important announcement page. You can find the YouTube link over there. You can go through the YouTube link and the sessions, and in case you have any query, you may you can put forward in the next sessions onwards. Thank you. Thank you all. So from tomorrow, we are having the session from 9:30. So we'll join, try to please join by 9:30. And for today, we are ending the meeting here. Thank you all.